thanks everybody for coming to my talk. So I want to talk today about two different things. I want to talk about first the tools we have in C++ for catching and handling errors. So this is more the C++ language part of the talk. And then in the second part of my talk, I want to talk about how we, especially at ThinkCell, use them in practice and have been using these tools for the last 20 years, as far as they existed. So who are we? I think you've seen us as sponsors occasionally. We are a Berlin-based company, a pretty successful company, I can say, and we have the leading productivity tool for creating presentations. So every big consultant companies, most Fortune 500 companies, they create a lot of presentations, for better or worse, and a lot of them use our tools to do that. And so we have a lot of customers. I've been doing this at ThinkCell for a bit over 20 years. And the reason I'm telling this is more because our application runs in a very hostile desktop environment. This is not an environment we control, right? Unlike you're doing a server application, the server is yours. You're doing embedded, well, this device is entirely yours. And in order to develop something that runs stable in a desktop environment, you have to have excellent error handling and especially error reporting. Stability and efficiency were key drivers of our success, I would say. But before I start with the meat of my talk, I first want to clarify some vocabulary. So we've talked this morning in the keynote, Anthony talked about safety, and he mentioned a couple of things that have to do with error handling, of course, right? He talked about how you have to be extra careful when you're running code on potentially dangerous devices, right? So when I think about, well, computers that run in environments where things can go wrong, I often think about these things, right? These do fly-by-wire controls, every single flap's controlled by a computer, and you have to be super careful that everything works all of the time. So this is like the hardcore mode of engineering, right? And when I researched this talk, I researched actually a bit how they do this. And just so you learn something in this talk, this is what I found. So modern planes have, of course, redundant systems. They typically have 3 primary computers, each of which can control the entire plane. And then they have a couple of more secondary backups. And now they are in completely separate locations in the plane, so in case you have a fire or whatever in one part of the plane, the others still work. And not only that, they also use diversified hardware and software. So you have them running on different chips. You have them running different software developed against the same spec. And they must survive hardware failures. RAM faults due to cosmic radiation, engine explosions, whatever. So this is what we call engineering for reliability, right? And developing safe systems that always run under all circumstances. What I'm talking about is a far simpler problem, to be honest. I'm talking about error handling, and in a narrower sense. And for example, I will assume that your RAM always works. I will also assume that your computer does not suddenly explode. And in a lot of cases, at least on desktop environments, error handling on embedded medical devices is something different. We can always resort to this, right? You've all seen the version of this. It's not great, but at least some software runs in not even security, safety critical environments. So we are doing this a little bit in easy mode. We deal first of all with an environment that behaves unexpectedly. So that might be our computer. Our operating system is suddenly behaving differently than from what we've observed before, from what the spec says. The user behaves unexpectedly very often, right? He's doing something with your tool that you didn't foresee. And we as programmers, I would like to say, we behave very predictably, unfortunately, and we do make mistakes. And we do have to deal with those mistakes. So all of these scenarios lead to software that doesn't behave the way you thought it would. And you need to handle that error. And you need to do this well, because bad error handling just breeds more bugs and your software gets worse. But what's important is that we can sink a lot of effort into this. We can sink a lot of effort into writing the perfect error handler that then in the end we never need. At the end of the day, we're not paid for writing the nicest error handling code. We are paid for delivering customer value. And that means we have to focus our efforts somewhere. The goal is not per se writing great error handling code. The goal is to get to a stable product as fast as possible. And having good error handling is key in order to achieve that. So first of all, I will talk about what tools we have in C, or C++ rather, how to use them, why they're important, why you should all use them. And then in the last part of my talk, I will talk about how we use them in practice, what's important in error handling, how to focus your efforts, etc. All these things I just mentioned. So let's start with the very, very basic, the thing that we have had since C++ existed, which is C-style error handling. So you've all seen this function probably somewhere in actual code, the POSIX open function. Takes a path and opens that file. It returns -1 on failure and sets the global error no variable to indicate the error. And then you look at the man page, well, what errors can happen? And there's a huge list. And they're not all the same, all these errors, right? There is the benign, end file does not exist. You probably have to handle this, right? This is something that can always happen. There is the slightly weird interrupt. Something was interrupted by a signal. For an open call, this means you can retry. For a close call, I don't think you can retry the close call. It's probably going to fail again anyway. And then there are the weird. Fault, path is outside the address space. That's probably not a runtime problem. Maybe I have an uninitialized path variable or so. But this is certainly a programmer problem. It's not of the same category as end, which is something that probably can happen all the time. So there's just a lot that can go wrong, a lot of different things. The Windows situation is very similar. Here's the create file function. If the function fails, we get invalid handle value. Again, the return value mixes error codes a bit and a successful file handle. And there's also a global variable, getLastError, that we can query. And this style of error handling also made it into the C++ standard. Here's the string to long conversion function, where you pass a string, the end pointer to the parsed end, and the base of the number you want to parse. And this will also, this will of course on success return the successfully parsed long. But we're interested in the error cases. So if there was no conversion, it returns 0, as if this weren't a valid long. It also sets the end pointer, and it sets the error variable to eval for invalid value, invalid input, maybe. There's an overflow case where your output will be clamped and an error variable will be set. And these are just a lot of things to check, right? A lot of things you have to check to make sure you're using this correctly, you're not missing a bug, you have to check them in the right order. So this is unfortunately relatively complicated. But we need good tools to handle these kinds of interfaces because, as far as we can see, they're never going to die, because this is the interface that operating systems are using now and will probably use for the foreseeable future, because the C-style interface always works. It works with every programming language. It is our lingua franca of programming languages, unfortunately. But, well, it's not great. So C++ invented exceptions, of course. Exceptions to have a better way to handle errors and to distinguish between an error value, this is the exception, it tells me what went wrong, and an actual return value for a successful case. But exceptions have gotten a kind of bad reputation. People call them a glorified go-to statement. They say it's difficult to reason about the control flow of your code if you use exceptions. People say exceptions are very slow. Some people ban them in their code base. So, for example, famously the Google C++ style guide says that the Google C++ code must not use exceptions. And I read it, I looked it up, and what they actually say relates to the last part I mentioned here. Exceptions, of course, require you to write exception-safe code. If your code is not exception-safe and you leak resources, well, you can't use exceptions. And this is actually what the Google style guide says. The Google style guide says, and I quote, "Our advice against using exceptions is not predicated on philosophical or moral grounds," which I understand as they don't think it's a bad technology per se, but practical ones. Things would probably be different if we had to do it all over again from scratch. And that means, and I think somebody confirmed this to me, that if they could write exception-safe code from the start, they would use exceptions. But they can't make their 1 billion lines of code, whatever they have, exception-safe, so they can't use exceptions. But exceptions can be an excellent tool for error handling. So here I have a very simple snippet of code. I see originally I wrote for CPP on C in Folkestone, and I never updated the string. And every line here in this little piece of code could realistically throw. We are making an HTTP request to some API, the network may be down. We are parsing something from a JSON response, the JSON response might suddenly be in a different format. And then we're writing something to a file, and the disk may be full. So here, every single line might encounter a failure, possibly from a very deep stack. Imagine you are writing a parser, a JSON parser that descends the JSON structure and builds up a deep internal stack. And without an exception, it has to return from that entire stack, check, oh yeah, I found an error, return, I found an error, return, I found an error, return. Exceptions make this much more elegant, both from the point of view of the JSON parser and also from the point of view of us, the programmers, who have written 5 lines of code that didn't have any error handling. And we just write this little catch exception phrase in the end. So we have what do you call it, a good path through our program that doesn't have any error handling code, and then catch an exception as close as possible to the location where the error might occur. And so I talked about, I don't know if you saw that talk, there was a very famous talk last year at CPPCon by Khalil, I forgot his last name, about optimizing the exception implementation in C++, because it was kind of slow and created very big binaries for embedded systems. And he optimized a lot of that away because nobody had looked at the implementation of exceptions in 20 years. And he told me that somebody came to him who had written a JSON parser and said, hey, look, we want to move that JSON parser from having return codes to using exceptions, because having return codes is actually also very, very slow if you have a deep path. So they had to do so many checks for return values on all these deep stack calls that this became a real, turned into a real performance impact. And exceptions would be much faster, because doing exceptions, having exceptions that never occur has almost no performance impact. And there was also Jason Turner, you probably all know, told me in that same conversation that he had once, I don't know, in some stream, he had ported Doom to C++, the old Doom code to C++. And then he wanted to experiment how big the performance impact of exceptions actually is. And in the innermost Doom rendering loop, he decided to switch some return statement to a throw statement. So abusing exceptions actually as a return value mechanism, just to find out if this would impact the Doom rendering performance. And it turned out that A, the answer was no, it was not distinguishable. And in the end, he found out that in every single frame of the Doom rendering engine, he had to throw, I don't know, 10,000 exceptions, I think, per frame, for this to be noticeable at all. So exceptions maybe are not as slow as we sometimes think they are. Exceptions have one very big advantage in programming, though. they can carry semantic error information, right? We can give them names, there are types. We can distinguish what was the HTTP error that was thrown, what was the parsing error, etc. Like I said, they keep the code clean on the happy path, and Bjarne likes exceptions for these very reasons, so who are we to argue with that? But of course, some of the disadvantages are kind of true. They can be slowish maybe on the error path. One important problem they have is that they are serial. That means you can only ever have a single exception that is being thrown and handled, and not multiple at the same time. And yes, you have to write exception-safe code. There's a great talk by Peter Muldoon about, well, the misuse of exceptions he found in practice at Bloomberg, with a lot of good examples on what not to do, and also a lot of good examples on how to clean up those misuses of exceptions. So that was exceptions. But now, wouldn't it be great if we could somehow marry the advantages of return codes, their simplicity, with the semantic richness of exceptions? And this was exactly the idea of Andrei Alexandrescu that he had in 2012 that led to the invention of std_expected. So this is what std_expected does. It is a very simple return value, but it contains a type that contains more information about the error, but it separates the return value from the error type. And making exceptions the error code is actually a quote from Andrei Alexandrescu. By making this change, we get a lot more advantages. We suddenly can have multiple exceptions, multiple expected errors in flight at the same time. We can store them, we can transport them across threads, we can group them together, save them now for later, we can transform them, all things we couldn't really do that well with exceptions, or at the very least, we could only do it with one exception at a time. So how do we use std_expected? So here's everybody's favorite error handling example, that's parsing an integer. I have a simple function that parses an integer from a string view, and it returns now an expected, which is either the integer or a parsing error. For simplicity, my error is just in enumeration. But here I'm not so interested in handling the errors in parsing themselves, but I want to process the return value further. So I'm parsing an integer, and now I want to return 1 divided by that integer. So here's the interface for std_expected and how to use them. I receive an expected. I can convert it to a bool to check if it contains the actual successful return value. I can then access this value. Here I'm also multiplying it by 2. Now I'm checking, is that value 0? If it's 0, I can't divide 1 by 0. So now I'm returning std_unexpected, so I'm transforming my error from the enumeration that I had before to a string, let's say a user presentable error message. std_expected is a generic constructor that is convertible to any kind of expected that has a string as an error value. If I don't have a 0 integer, I can just create a std_expected of double and string, which is 1 divided by that integer. If my original parsing call was unsuccessful, I end up in this branch, and you can see I can switch on the error that was contained there. I can just access the error and do the same conversion of the error enumeration to a string. So this is the, let's say, conventional imperative programming interface that std_expected has. It is simple, but it's not super convenient. There is a much better, much more elegant interface of std_expected, which is the monadic interface. The monadic interface means that we have a couple of functions on std_expected that allow us to transform the contained value in a few defined ways. So we have, for example, the transform member. The transform member takes a function that is only called when the std_expected contains the successful value, the integer. Then this function will be called. I can chain this with a transform error. This will only be called, of course, if the std_expected contains the error value. Now I can transform my error into something else. And then last but not least, we have and then, like on optionals now. Again, this is only called if the std expected contains an integer, and I can here transform my std expected on an integer into a std expected on another type here on the double by doing this division thing. So this is what I think is the much more elegant interface. It doesn't have any explicit flow control statements anymore. It's a very simple transformation pipeline of a type into a different type. Makes it very easy to see that we didn't miss a case in that long list of if-then-else statements. That makes it much easier to think and reason about the program state, and it just makes it harder to make mistakes, which is what we're here for in that talk. And I think that std expected is going to be the, let's say, standard way of handling errors in the future, because it is a very simple and powerful way that we didn't have before. Now there's another new feature that is new in C++26 that is related to error handling, specifically related to handling programming errors. We've also heard about this morning in the keynote already, which is contracts. And the contracts proposal is a fantastic proposal by Timo Dumler and others. It's a very long proposal, it's a very thorough proposal, because they took a lot of care to get feedback from the community about how people already implemented contracts, how they used contracts. Timur has also talked to us about how we do error handling to improve the contracts proposal in the future. So it is very long, very thorough, but it's a very conceptually simple idea. He himself has written a small blog post that explains contracts in indeed roughly 5 minutes. And contracts are not for handling environment errors. We won't use contracts to check return values of functions, but it's a more flexible and the new standard assert mechanism. And we will be using it in the place of the old C-style assert macro. It allows us to express invariants and pre- and post conditions on functions. And one very important feature of contracts is that it allows us to customize the behavior of these assertions at build times. So the old assert macro was either on in debug builds or it was off in release builds. And here with contracts, we get to decide at build time what should happen. I'll get to that in a moment. So this is how contracts look in practice. It is very simple. We can annotate our functions. Here we have a very simple function, just returning x plus 1. We write a precondition like this, and here we assert for some reason that x is not supposed to be 0. So this precondition captures the function arguments, of course, and these function arguments are implicitly captured as const references, so we don't, by accident, manipulate our inputs in our asserts. And we can also define post conditions, and post conditions can capture the return value. So here R is implicitly the return value of that function. And the post condition can also capture the function inputs, x. But if we do so, then x must be declared as a const input. It's just to make sure that we haven't manipulated our function inputs ourselves inside the function body, and we're still talking about the same thing. So these are very sensible decisions, I would say. And then we also have, as a new assert mechanism, we have contract assert, which is just like the old assert, but better, to assert any other kind of invariant. So when are these contracts evaluated? The preconditions are evaluated after the function arguments have been initialized, of course, but before the function body runs. The post conditions are executed after the return values have been initialized, because we can access that return value. But before the destructor of local variables run, they again might change some state. Contracts support exceptions in the sense that throwing an exception inside a contract evaluation implies that the contract has been violated. And interestingly, because this is, well, it's 2025, but this is C++26, They are supported in const expr contexts, of course. And so you can use them in const expr statements, and if your const expr construct violates a contract, this leads to a compile error, of course. What else? But here's the most interesting feature. So we can customize their meaning at compile time. And there are 4 different semantics that we can choose from. So at compile time, we can say, well, in case any contract is violated, I want to do nothing. So this is the old assert release behavior. I want to observe the violation, which means that a contract violation handler will be called, it can log whatever, but program execution will continue. We can choose enforce semantics. Enforce semantics means we are calling a contract violation handler, again, to do logging, reporting, whatever, and then we will terminate. And quick enforce means terminate as quickly as possible. And there's a very simple, well, intuition on who uses what, and we've heard a little bit about it again this morning. So quick enforce is you are a medical device, right? Something is going wrong, you are somewhere going off spec, you terminate, which in practice probably means restart. Enforce means, well, you're maybe Bloomberg, you're handling money transactions, financial transactions. So you have enough time to say, okay, something went wrong, I will log this because I have to find out what caused this, but I'm not going to do any more transactions and I'm terminating myself here. I don't want to lose $1 million because of this. Observe is your typically a desktop application, for example, right? Not very security relevant. And then how do you say that? The decision we can make is we have a contract violation, and we can terminate right now, which might be more secure, but it's certainly going to make the user unhappy because we're crashing now. Or we can hope for the best and see if we can continue running, right? We might crash as well. We might not. And then the user's a little bit happier. So this is what desktop applications typically do. And the reason is that all the contract assertions that you write, they're code too, and they might be wrong. So it might be better to keep on running and just hope for the best. And we want people to write all those contract asserts after all. So you can also customize the contract violation handler. So this is the function that will be called in case a contract is violated, obviously. So you get an instance of the violation, you can check under what violation semantic you are running, and then you can, for example, defer to your own error reporting mechanism and can say, hey, I encountered this error, log this somewhere, send a message home, whatever. Contract assertions are allowed to have side effects. Logging, for example, would be a side effect. But the paper says they're not allowed to have destructive side effects, which is kind of a not very well-defined difference. I think the difference is a destructive side effect would be a side effect that changes the correctness of your program. So your program should, of course, still be correct if all contract asserts are disabled, if they are evaluated in a completely different order, or just a few of them are evaluated, because technically they don't want to guarantee that all of them will be evaluated all the time in the same order. So they should have no effect in a correct program. And of course, there's zero overhead. This is C++. There's zero overhead if you choose ignore semantics. And yeah, these are, I think, the important aspects. And contracts have one great use case, I think, in the future. Currently, I think a lot of people might have code like this in their code base. You use some external library, Boost in this case, that has its own kind of assert for error reporting for, well, essentially enforcing contracts. And so you have something like this somewhere in your code, in some header that says, yeah, Boost, please use my assert handler instead. And now, if you do this for a lot of libraries, and I hope they do have asserts in the first place, it's much more convenient if they would all use contracts, and you would define one contract violation handler, and all external libraries would automatically use that one. That would be really nice. And so speaking about using contracts, this is the last C++ feature I want to talk about, we have hardened library implementations now. Hardened library implementations exist practically for the 3 major compilers now. And a hardened library implementation is a standard library implementation that actually enforces the pre- and post conditions that have always been written in the standard, but, well, we never enforced them, right? So the standard says you can't dereference an end iterator, for example, but in practice, of course, you could. It would just crash, and there was no assert. And this library hardening proposal is based on contracts. So in the future, whenever one of those STL asserts is violated, they should be calling a contract violation handler. This is not the case so far, so due to a lack of implementation, of course. But all 3 compilers do have a hardened implementation. On Clang, on GCC, on Microsoft, Microsoft had a similar iterator debug library for a very long time. So iterator, that was even more powerful actually than what I think the hardening proposal now enforces. So they always checked in debug builds that your iterators were valid, you were comparing iterators that were referring to the same container, etc. So they had a lot of metadata in debug builds to check for correctness. Okay, so we have a lot of options for error handling, for writing correct code, for checking that our code is correct at runtime. But we have so little time, right? Because, as I've said in the beginning, we're not actually paid for handling errors. We are paid for solving customer problems. And the goal is to get to a stable product fast. And we want to write good error handling code. And that means a few things. Error handling must be easy, otherwise your developers won't do it. The error handling must be tested, otherwise it doesn't work. Error handling must be focused on where it matters, otherwise you waste your time. So how do we achieve all of these 3 things at the same time in practice? So this is how we do it, right? This is how we did error handling for the last 20 years. So the first rule is we check everything. We check every single return value of every single API function we call, of course. And so here, for example, get hostname on POSIX systems sets the error variable. In the success case, it would return a 0. If it's not 0, check error, tell us what the error was. Similar on Windows, there's this certain standard Windows API error protocol. I think they return also 0 on success. And otherwise, call getLastError, tell us what the problem was. So we check every API call, and we make this very easy. There is a different wrapper for every error reporting mechanism that those operating systems have. There's error, there's getLastError. Windows sometimes has hresult error codes. There are Mac kernel errors, everything you can imagine. And since this is the first thing we typically look for in a review, especially with newer colleagues, did they think of all the error handling, error reporting calls, there's also a returns void to make sure that you can annotate that you check this and it doesn't return anything. And I didn't forget the error handling, there is none. So it's returns void. It annotates that a function returns void, and it statically asserts that it does actually return void. And we also use asserts aggressively, our own assert, because they stay in release builds as well. We also use noExcept by default to make clear which parts of the code are actually allowed to throw exceptions and which ones aren't. So there are no unexpected exceptions. Writing a noExcept in a place where there shouldn't be a noExcept might lead to a std terminate, of course. But the reasoning is, again, it's not so security relevant where we work. I think Bloomberg doesn't do this. Bloomberg does not want to randomly crash when somebody throws an exception. In this case, they hope for the best, I guess. But throwing an exception that doesn't have a handler in the end will lead to termination anyway. And we do install a std terminate handler in the runtime to make sure we are notified when somebody calls std terminate. Okay, now we check everything. We have a lot of error checking statements in the code. What do we do with all that information? By default, we don't do anything. By default, we assume everything works, unless we could prove otherwise. And the goal is that we want to have a small set of possible code paths. We want to make sure which things actually do happen in practice and which things never happen, because then we don't have to think about them. And the only exception, of course, is the cases, well, you know something can fail, right? So dealing with files or networks, for example, these are or user input. These are the cases where you always have to assume some errors happen. And again, then you have to make it easy. So this is how it looks if you try to open a file with our error reporting stuff. So opening a file has several different scenarios. If open file returns non-negative value, that's a success case. That's a file handle. Cool. It might return an invalid file handle and set einterrupt. That's the case where I have to retry. So keep retrying. And then there are the cases where I know these can happen because they're just expected situations. The file doesn't exist because somebody deleted it. I don't have access rights to them because the administrator took it away from me, or the disk is full if I'm writing. So these are things I must handle. These are not exceptional. These are just expected behaviors. But everything else is considered an error that never happens. I don't have handling code for this. I just get an error report. We'll talk about this in a second. The situation is similar, of course, on Windows. Here, removing directory, there are cases that will happen. The directory has already been deleted. So what happens now if any of those checks fail? So if any of unexpected errors happens, we try to collect as much information as possible. And this means that we will send an error report to our backend. So we have an error reporting infrastructure that on the client, even when you're just encountering a failing assert, runs an error handling process that for a short time pauses the process that encountered an error, collects as much information as it can, for example, a stack trace, a stack dump, and sends this to our backend. On our server application, which is just our internal server, it will hold the threat and notify an administrator by email. And then again, we try to carry on somehow. So this is observed semantics in a way. But we do think that the behavior of our program is now undefined. Something happened where I thought it would never happen, so I'm not sure what can happen next. So I will disable any further error reports. But we do not terminate. Asserts can be our code, and they can be wrong, and I want our developers to write asserts. So I don't want to punish them by having customers call saying, oh, these assert messages pop up all the time. Please do something about them. So like I said, this is observed semantics. And then we try to focus on the areas that matter most. So we have collected now all these mini-dumps, all these stack traces of assertic failures, of unexpected error codes, and we collect them all in a database, and we can analyze them and query them and find out what are the locations in our code that encounter the most problems. Where do I have the failing assert that fails the most often? I can drill down what operating system does this happen on, which version of my software does this happen on. And yeah, we can do some filtering, can look at where in time does this happen, on which versions did this happen. These are the little graphs. And then I get more information. So I can find situations that only happen in the field, bugs that I could never reproduce in-house. But you ship this thing to 1 million customers or more, and they're running this in Korea with Korean keyboards and text inputs and input managers or whatever, and suddenly you have a problem you've never seen before. And then I try to reproduce this mistake. So we find all these mistakes that depend on different user environments, right? And then we try to reproduce them. And then we add handling code for the things, the problems we could reproduce after all. Which means that we have error handling code that is always testable, because we always have a reproduction for something that was failing. In practice, very few of the error handlers have encountered or solved most of the problems. So we can focus our effort on writing good error handlers that don't just show a message, something unexpected happens, sorry, but maybe they can implement a workaround. They can fix the problem. Maybe the problem is in our environment and we can do something about it. So we can actually fix some of those problems. And then we, as like a further step, we have different categories of errors. This is something that Timo wanted to know about for improving the contracts proposal, so I hope contracts will get something like that. So we have different categories of errors, and they change the behavior of our error reporting system a little bit. So we have critical errors. These are errors like null pointer access, API calls returning an unexpected error code, or failing assertions. These are indeed things that should never happen. Where we don't have handlers, it's a programmer error. The program is invalid afterwards, like I said. So we will disable all further reports and just hope for the best and keep on running. And then there's a level below that where we have a situation maybe like this here. So you get an input range and you want to find out what Unicode value is that range of bytes. And conceivably, that range of bytes might not be any valid Unicode value. And I say, I don't know how this could happen, but I think it does happen, or it could happen. And then we have like a special error handling annotation. And here the handling is very simple, because the handling means, well, I can just always return this replacement character if something goes wrong. So I have handling code that is so trivial that I consider this good, tested, good enough, even though I actually don't know how this could ever happen. It can theoretically happen, and if it ever does, I want to have an error report. But we don't disable further error reports. We consider our program is still in the land of defined behavior and just keep on running. And then we have a couple of error levels below that, maybe a third-party bug where we think, okay, well, where this is a bug in something we interact with, but it's something we have reproduced, we support, we have a workaround for, and that is tested, but somehow this degrades the user experience. So users might complain about it, and then they call our support team. So this is a bug that we will always log in user log files. We never report it to our backend. That will be wasted effort. But if the user ever calls our support team, they can just look at the log files and say, ah, yeah, you have this and this and this problem, and it's not our fault, I guess. Yeah, complain to somebody else. And similar to that might be a weird environment configuration. On Windows, surprisingly, you can configure the space character as the decimal separator, for example, which I don't think anybody does on purpose, but people do this by accident. And not all programs support this really well. And we found this out and then reproduced this, test this. The workaround works, but still, it's something that might surprise people and they complain. And so this is something we would, for example, only log in debug builds. So if a support engineer has contact with that user and the user complains about something, they can flip a flag and then look at the debug logs as well. Okay, and then I said we do this error reporting that sends a stack trace to our backend. And this is similar to Google Crashpad, for example. There is at least that open source solution. I'm not sure there are others. And what they all have in common is that they typically do out-of-process handling, like I said. So you start an error reporting process that pauses the process that had the error and then gathers the stack information, etc. You have to do it out of process because, well, your main process just encountered an error, so you are not sure what state it is in. It's not safe to do error handling in that process. That might not actually work. And we then create mini-dumps, so little informations about the stack and the loaded libraries in an operating system-specific format. There's a bit of open source code how to do that on macOS. So you get little dumps that are just 100 kilobytes or so, but you can load them in LDB, and then they contain, well, they show you the stack. On Windows, that's a standard feature in the debug libraries. And then we upload that dump and have it in the database you've seen. And then we do even some server-side analysis on these things. So we open all these mini-dumps on the server, we symbolicate them, we load them in a programmable debugger, and for example, we can identify the last relevant stack entry. And we can group all the errors by what function that was, by what line number in that function, so we can, well, show meaningful information to developers and can point out, like, this is the part of the code where we are currently having a lot of assert failures. Look into that first. And then we end up here, and we can fix all these nice bugs we would have never seen before. And that is the end of my talk. Thank you very much for listening. And we now have pretty much exactly 15, 14 minutes for questions.
Is that okay? Yeah, thank you very much for the talk. I want to get back to what you had showed up the beginning, comparing these different methods for dealing with errors, and you covered exceptions, you covered using standard expect, you used C error codes, and as I was looking at that, and you focus especially with exceptions on the happy path.
Yeah.
The exception example was by far, in my mind, the cleanest happy path of any slide you showed.
Sure.
Up to then and thereafter. What I didn't quite see is using your error handlers, which look like they're macros, right?
Unfortunately, they are. I think not all of them would have to be. I think some of them we could change. But for example, the ones checking the error variable, here, this one, this does a retry. So you actually do have to generate code with a loop checking the return values and the error variable, and inside that loop, you have to do the open call. So you could write it without a macro, but then you would have to wrap the open every time in a lambda, which would be kind of annoying. So you could do it without a macro, of course, but it would be a bit more annoying to type.
Okay, but then from what I could gather from the approach you're taking, you don't really have a happy path here. I mean, you only have one statement that's wrapped in an error handler.
This is only the, in a way, oh, sorry. Well, this is all the happy path. This has very defined behavior. It will open the file or it won't. If it won't, it is because of one of those 4 errors.
Yeah, but I mean, there's only one statement actually.
Yeah.
That's happening, whereas in a try clause of an exception style method, you would have several statements, and the one or the other may or may not have anything to do with each other.
Yes.
It's just, you know, you do 1, 2, 3, 4. If there's a problem, well, you end up here.
Yeah.
Okay, I wanted to make sure that I understood that. So from what I could gather out of your talk, the problem with exceptions, given the feedback from Jason Turner, is not so much that they're necessarily slow. It's the difficulty in writing exception-safe code.
Yes, and in using them in the right places, I would say. So my example, I think, was exactly the example where we do use it. So where I think you should only use the exceptions in places where the control flow feature is actually what you need, right? So you do a couple of things in order. And if one of them fails, you don't need to do the other ones. Or the example where I talked about that you are actually exiting from that entire stack. And in those cases, this control flow part is a feature. But then you have to catch it somewhat locally, right? If you let this flow through your entire program, then it does get hard to understand. So there is a there's a way to use them correctly, and then they're a good tool, I think.
Okay, well, thanks very much.
Thank you.
So I have a question from the online crowd. Working on safety critical systems that require all the code analyzers, Misra tends to developers that cope a lot with code style issues and branch coverage. But thinking about the architecture is dropped too fast because no tool checks that. And refactoring is really extremely expensive now. Is that good?
Not sure I know what the well, I'm not sure what the question is in the end.
Then I'll give you an alternative one. Can you explain a bit more about hardened libraries and its usage?
Oh, yeah.
Is it used for testing purpose or in safety critical production code?
So I think it is definitely used in testing code. So I mean, in testing, that means with debug builds, etc., you typically want all the error reporting features on, right? That's why you're doing testing. You want to find out in testing that something is wrong. So I think, for example, in Xcode, I know that by default, the newer Xcode versions already enable the library hardening feature in Clang. So it will not only crash, the problem is it might not crash, it will really tell you if you're doing a call to a standard library function and you're violating a precondition. So famously, dereferencing an invalid iterator will not randomly crash, it will tell you you're validating an invalid iterator. And the question, if you want to enable it in a production build, I think is the same question as what your contract violation assert mechanism in release builds is in general. So we would enable it in release builds, because even in release builds we have asserts and everything, but not everybody does. But I think if you have the choice, you probably very often, well, you want to know about it, but if you then crash or continue, that depends on your application scenario.
Thank you very much.
Thank you for the great talk. I really like your approach in trying to collect rare errors in rare customer systems, especially if you have so many. My question is about macros, because that's like, well, something some people think shouldn't even exist in C++. For example, the project I work on has basically a rule, no new macros. Because they become unmaintainable really fast, and here you propose them as a solution to your problems. How do you address the maintainability of this thing afterwards? Thank you.
It's a good question. We try to minimize their usage, of course, and I don't think we have that many, and some of them we could replace with reflection in the end. So error reporting, I would say, is one big one, where, like I said, the reason we need them is that you sometimes have cases where you need to do the code generation, and then the open call here could be a lambda that you evaluate in the right place, but who wants to write the bracket, brace every time? So here, I think the fact that this is a macro is like a very small convenience feature. Right? We're not building a huge contraption that nobody understands anymore. We have more code generation for other parts, like having a persistence library, for example. And this is maybe the classic example where you wanted code generation. Now we just write a macro around every member or something like that, and then they generate the persistence code. And this is something we could probably replace with reflection, and I guess we will once that works, right?
Thank you.
But yeah, otherwise, I mean, they're also a bit fun, aren't they? I mean, I don't want them for the future of the language, but the Boost preprocessor library is kind of cool.
Hi, thanks for the talk. I actually had the same question, so I'm asking another one. And this other question is, with stood expected, can you propagate the result of the stood expected to a higher level function, to the caller, so that you can relay that even further and then delay the error reporting to a more remote
Sure, I mean,
function?
I would say this is what they are good at, right? My example tried to show a little bit how you would do that, because what motivated this example was exactly that idea that you have that you want to transform errors very often, once you like transport them upwards, right? Here I have maybe parsing the integer error, and that's a very detailed error, and then further up the chain, I actually want to have maybe a user visible message or something. So not only can you return them, because they're just in return code, but you can easily transform them and change their semantic meaning and maybe, I don't know, group them inside each other, right? So the way we did with exception, you have a big application exception, something went wrong, and then you have the detail inside if you know where it came from or whatever. So yeah, should group them, transform them, move them upwards. Yeah.
Okay, thanks.
Sure.
Another question from the online participants. Since we are talking about safety, I'm wondering, while Rust offers the same low-level performance as C++, but also provides compile time guarantees for memory safety, data race safety, etc. Given this, why do we still choose C++ for safety-critical software instead of switching to Rust?
It's a fair point. I could take the easy answer and say this is a C++ conference. This is what we're talking about, C++. Once Rust gets that level of usage, I might say. But I think one reason, and I think this is always a bit overblown in this comparison, is that Rust offers better protection against one very specific class of errors. They are relevant for security issues, maybe in distinguishing them from safety issues in general. This is about security, about memory security, about them being exploitable, etc., but also at a cost. It is a performant general purpose programming language, but it has a very strict way to enforce that also restricts your programming model. So I'm not sure this contrast between them, I'm not sure they are so interchangeable. That's I think, my answer. And this is why we're talking about C++.
I think we can handle one more question. Hello, you mentioned that for safety-critical software, we need an evidence that the software is safe. Could you please briefly tell how that works in practice? How is it being done? I think so.
That doesn't sound like a question to my talk.
Sorry, can I just make one comment about one of the previous questions? It was on the hardened libraries. There was a great talk last year by Louis Dion and one of his co-workers here at Meeting CPP.
Right, because he worked on that, I think.
He worked on that for Clang, I think, and so everyone can go and watch that video to find out more about how that actually specifically works.
Yeah.
So this standard expected seems similar to some primitives we have also in different programming languages, like result and so on and so forth. Mm-hmm. And is there any primitive for doing some sort of asynchronous operations within these and then chains or something like that? You know?
I am pretty sure that they are not by default anything that is async. I would have to look, but I would guess 99% I'm sure that these things aren't mixed. If you want to do something async, then use one of the async mechanisms in C++.
Okay, thanks.
Sure. Okay. Well, if there are no more questions, then thank you again. Thanks for having me.